All right, today I want to explain the role of oxidation and reduction within the production of ATP or energy through this formula here, the cellular respiration formula. So it's just glucose plus six oxygen, because remember, oxygen is a diatomic molecule, so it's only found by two. So in reality, you have 12 oxygens, like singular oxygens. Um, and then that's converted or that's reformed into six carbon dioxide, six water molecules, and the golden prize, the thing that we wanted, ATP. Right, this is our goal over here. This is also better known as energy. Right, it just carries the energy that is going to be used throughout the cell. So let me just change the color here, not white. Let's go with that. So this is just the energy. Okay, my handwriting there was very bad. Okay, so this is just the energy. Okay. Okay, so now to understand this, it's very important to understand what oxidation states are. So an oxidation state is basically the potential charge of an element. So let's, for example, take a look at this over here. Or you know what? Let's take a look at this one over here. Okay, so let's take a look of an individual carbon dioxide molecule. Okay, so you have something like this. So if I were to draw this out as like a um, within a diagram format, let's do something like this, right? So basically, you have the excuse me, the carbon needs a 4 plus charge, right? um basically to become stable, and then the oxygens need a 2 minus charge. So an oxidation state, what it basically states is what if potentially these bonds do not exist, right? What would their charge be? Okay, so what charge would these specific elements be? So in our case, right, this would become 2 minus, this would become 2 minus, and this would become 4 plus. Now it doesn't always necessarily have to be in this particular case. It's mainly due to the fact of electronegativity. All right, so that's another fancy word that we need to learn about, electronegativity. So the oxidation state is basically based off of the electronegativity. And again, this is not the oxidative state is not what is actually existing in real life. It's basically just giving us kind of like a blueprint or a guess of what would happen. So and this is going to be more important when I talk about oxidation and reduction. But anyways, as I said, oxidation state is the hypothetical state a element would be like in when you're in a molecule, right? The hypothetical charge it would be if these bonds were to break. So if these covalent bonds were to break, right? What charge would this element specifically be? So in our case, it would be -2 here, right? It would be -2 here, and then it would be +4 here. And there's actually a really good reason for this. So there's a reason why. And that reason is because of electronegativity. So oxygen, and you can look at the periodic table like from the area of oxygen and the area of carbon. So basically that'll kind of dictate the electronegativity. And basically the electronegativity states how willing or how stubborn, you can say, I'm oversimplifying it, but how stubborn a specific element is. So basically, it's the capability of that atom or element to hog. Let me hide this here. To hog electrons. Okay, so the more electronegative you are, the more you hog electrons. All right, so in our case, right, oxygen is more negative. That means that in theory, these covalent bonds are going to be allowing the electrons to share, like between the carbon and the oxygen. But in reality or in practice, most of the time the electrons will be in the oxygen area, and that's simply due to the fact that oxygen is more electrical negative. That means it will hog the electrons more. And so that's why if these bonds were to break, the electrons are more likely to go to the oxygen because the oxygen is just naturally more inclined to get them due to that electronegativity. Okay. And then that's also the reason why this is positive. Positive means again you have you need more like you lost electrons, right? That's the way I could say it, best explain it. So you've lost electrons. So if you have a neutral, like electrically neutral atom, and then eventually all of a sudden it becomes a positive 4 charge, that means you lost 4 electrons. Because remember, electrons is a negative charge. So if you lose them, you're actually gaining a charge, right? Because remember, basic mathematics, negative with a negative equals a positive, right? So anyways, so that's also the reason why carbon loses electrons, and that's why it has a plus, like a positive charge. Because if the electrons that are being shared here um, go to the go to the oxygen, right? Like in this case, it'd be 2 electrons. So the 2 electrons from each of these covalents, if these covalent bonds were to hypothetically break, they're more likely to go to the oxygen, and therefore the carbon would lose those electrons, and it would lose 2 from each of the specific elements. So again, oxidation states is basically a hypothetical. I like to think about it like when you get married and divorced. So let me actually show this properly so you can explain it. All right, there we go. So basically, when a person gets married, let's say two people, they get married, right? So they're in love and they get married, right? What happens is, let's say their money. So let's use the context of money. So let's say their money, it gets shared, right? This is the same way how in our covalent bond, we're gonna just use this over here. This is obviously a marriage between 3 entities, but it's okay. Uh, it's just an analogy. But anyways, the point is that okay, you have these two people who love each other and they get married and they share their finances because they love each other, they live with each other, they trust each other. Same thing when these bonds happen, right? When these bonds happen, electrons are being shared between two parties, right? So in our case, these two parties are sharing these electrons, right? 2 electrons to be specific, and then these two parties are sharing these 2 electrons. Okay. Now let's say they get divorced. Okay, so let's say they get divorced. This bond is broken. What happens to the money? Well, let's say they had a prenup agreement, right? They had a prenup which stated who gets what, right? So let's say this person gets $100, and then this person loses that $100, right? So one person gains that $100, one person loses that $100. Same thing here. The oxidative state is basically the prenup of this bond, right? It's basically where would these electrons go if these bonds were to break. So if these two bonds were to break, since oxygen is more greedy, more negative, that means that it is more likely to take these 2 electrons, and therefore this carbon will lose those 2 electrons. And same thing here, because you have an oxygen again it's it's higher in electronegativity. That means that those 2 electrons will be lost by the um, carbon and then gained by the oxygen. And then therefore that's why this would have an oxidative state of 2 minus, and then this would have it as 4 plus. Now, if we look at another example here, let's say we look at the example of O2, so oxygen 2. In this case, the oxidative state would actually be neutral. And the reason for that is both oxygens, again, we're basing this off of electronegativity. So these both oxygens are negatively equal, right? They both are equally as greedy. So therefore, when they break, that would never happen because again, oxygens are diatomic molecules. But in like theoretically, if these two were their bond were to break, well, their oxidative state would be 0, and when they break, they would both be at a zero charge because they both would hog the same amount of electrons. Because again, they're both as greedy, or they both have the same capability of hogging electrons. So now that we understand oxidative state, let's move on to more about the specific reactions. So now to understand oxidation and reduction, like how it's applicable, excuse me, um, to cellular respiration, it's important to understand the key basics first. So oxidation is just the losing of electrons. Okay, so you lose electron, and then reduction, if you haven't guessed it already, it's the exact opposite of that, right? So reduction is when you oops when you gain electrons. All right. So oxidation, you lose electrons. Reductions, you gain electrons. So now within our specific chemical equation, we will actually use the oxidation state to figure out how much uh, within the oxidation and reduction reactions or processes, how much electrons are being lost and how much electrons are being gained. Okay. So here's how it goes. So within our cellular respiration formula, what is being oxidated is carbon. So you have a carbon molecule here, right? Um, so it's C6, right? And that C6 comes from the glucose molecule, right over here, right? And so that C6, right? What happens to it is when you now we have to look at the so this is the reactants, this is the products. So we have to look at the products. What happened to that to those six carbons? Well, to figure out what happened to them, we have to look at where they are now, right? And this is why it needs to be balanced, because you need to have the same amount of um, atoms on each end so that you can do the oxidation properly, right? So here you can see that it's over here. So it's in the form of six, like that, six individual carbons. So these carbons are actually bonded with, like, within a compound. This six carbons are separate, right? There's separate carbons, and they come from the CO2. So now this specific element here has a four positive oxidative state. So basically, what that means is that if this carbon molecule were to break apart, this carbon, this carbon dioxide molecule were to break apart, this carbon uh, um, atom would have a four positive charge. Now, what that tells us is that this is oxidation, by the way, so that means we're losing an electron. So, therefore, how many electrons do we lose? Well, we have six of these carbons, and each of these carbons have four plus if they break apart from their CO2. Therefore, we lost 24 electrons because you have to do six times the four, and you get 24 electrons. And we have to write it in this way because you can never write a minus sign in chemical equations. So we write C6, which turns into the six carbons, which have a four plus oxidative state, and then a second entity is the 24 electrons that we lost, right? So we lost it from these six carbons. So these six carbons lost those 24 electrons when they became oxidized, right? And again, this happens because they're now a part of this molecule. So they're sharing electrons. And when they're sharing these electrons, hypothetically, the oxygen will be hogging the electrons for most of the time because it's more electro negative, right? It has more capabilities of hogging it more. Now for the reduction happens with the oxygen. So you have oxygen, and then that oxygen so you have oxygen, and then you have another form of oxygen as 6O2. So this is coming from the glucose, and then we have another form. It's coming from the other part. And so that turns into um that turns into plus 24 electrons, and then we see that in the form of 6O2, and then plus 6O2. And then you can see that this O2 is actually coming from this, don't ignore that. But you can see that this is actually coming, this 602 is actually coming from this equation here, because it's coming from over here, right? This is where it's coming from. So therefore, this is actually has an oxidative state of 2 minus, and then this has an oxidative state of 2 minus as well. Oxygen usually has a 2 negative like state because it's so electronegatively inclined, so it will always gain the two electrons it needs to become stable, like its valence electrons to become stable. So basically, this balances the whole equation out, because you lost 24 electrons from oxidizing the the C6, right, the carbon, but you're gaining those electrons back in the reactants because of the fact that these oxidative states are too negative, right? So yeah, that's why you gain over here. So therefore, you have basically, to conclude, you have your cellular respiration. You have your carbons, so your carbon atoms. Oops. So you have your carbon atoms oxidizing, so they oxidize, and then you have your oxygen atoms. Your oxygen atoms, they are reduced, or yeah, they are reduced. All right, and this is all has to do with hypotheticals, and it all goes back to oops. It all goes back to oxidation states and having the hypothetical charge, right, associated with each one of these things, right? So now you have these the surplus of 24 electrons that can be used. All right, and so these 24 electrons are they're stored within these oxygen molecules, specifically these, right? Right. So when these are to break, like when these things are to break, what would happen is also, this doesn't have an O2, by the way. I just realized this doesn't have an O2 because it's part of the CO2. But so this whole, like these two specific species, they have 24 electrons, right? They have 24 electrons, like a surplus of 24 electrons that they can use. All right.